Okay, today I have the pleasure to introduce Antonio Arribas. He holds a PhD from the University of Michigan. He has over 20 years of experience in the mineral exploration industry across multiple companies, geographic regions, and positions, including Vice President Geoscience at BHP in Singapore, Senior Manager of Geoscience at Newmont in Colorado, and Exploration Manager at Placer Dome. Currently, Antonio Arribas is a professor in economic geology and the holder of the Kenneth F. and Patricia Clark Distinguished Chair at the University of Texas at El Paso. In 2013, Antonio Arribas served as a president of the SEG, where he continues to be a member. Today, Antonio will bring us geoscience exploration talk about how advanced argillic alteration can help to interpret alteration zonation during an exploration survey and how can be used to support the assessment of epithermal and porphyry ore deposits. For example, does pyrophyllite indicate a residual quartz feeder zone or deeper proximity to the top of a porphyry? Stay tuned with us and you will discover the answer. Antonio, the next 45 minutes are yours, and I'm really looking forward to hear what you have to say.
Thank you, Filipa. Can you hear me well?
Yes, yes.
Thank you very much. It's a real pleasure and honor to be here. So I will hello to everyone around the world, and I will cut my video to make sure that I have my full bandwidth. Okay, so welcome to this seminar on naturalist painting in the Western United States in the 19th century. This is what you wanted, Filipa, wasn't it? I don't think so. Anyhow, you will understand. I'm just kidding. You will understand why I show this painting of the Grand Canyon of the Yellowstone for the topic of this talk. I want to emphasize this is a talk that follows an earlier one by Jeff Hedenquist on epithermal deposits earlier this year in the series of our deposit hub. And this is a joint project, it's a joint work we are doing, and will be a paper very soon. So the talk is about three topics. The first two are in part of the title: diverse origins of advanced argillic alteration and the exploration implications of these origins. The third one is more practical, more for students actually, and it's about recommendations on the use of this term and essentially any other term. And I'm going right away, I'm going to go to this point, to the recommendations on the use of the term. I'm going to illustrate this with an example. I'm going to go to the island of Lihir and the Ladolam gold deposit of the coast of Papua New Guinea. As most of you know, this is a deposit in this hosted in a volcanic island within what used to be a collapsed volcano. What it is, a collapsed volcano with two main deposits, lineage and Minifee, and you can see these bright white and yellow colors. We are talking about advanced argillically altered rocks. We also have this geothermal venting. This is a geothermal area. The deposit is extremely young. It's just less than half a million years. So this is a classic example of a magmatic gold mineralization in a magmatic hydrothermal system, essentially within the heart of a volcano. And that's the geological environment we're going to be looking at today. So an alteration map of the Ladolam deposit I found recently in the excellent book by Walter Pohl, Economic Geology, the second version, and this is the map in the book, in page 231. So I highlighted in red the color of alteration associated with these two deposits. We were looking here from the west towards the east. And this is the Louise Harbor, and we have what is labeled advanced argillic alteration. Silicification, argillic alteration, advanced argillic alteration. It's a simplification of the original figure. Well, what is the original figure? Paul refers to a paper by Gemmel et al. In 2004. And I show a frowny face because, unfortunately, this is an unfortunate simplification, as you will see. So we go to the Gemmel et al. 2004, and what do we find? We find this figure which refers to Moyle et al. 1990. Essentially the same figure, the same simplified patterns in the legend. We go to Moyle et al. 1990, and we see essentially the same figure, a little more complex. The legend shows many more units, but this red unit continues to be advanced argillic alteration volcanics. And they refer finally to a Davis and Valentine in 1987. Now we are talking about 33 years in the process between the figure in the textbook today and the original figure. So let's go to the original figure. This is the paper by Rod Davis and Jeff Valentine with the short source of typical of the 1980s. These are the guys who describe the original paper, the original deposit. And here I don't have a frowny face anymore. I have a smiling face because the same unit, the same alteration is not labeled advanced argillic alteration, is labeled white rock composed of opal, alunite, and kaolinite. If you read the paper, even I think in the legend, it says that this is a porous rock, white porous rocks consisting of opal, alunite, and kaolinite. And that, for those of you who have familiarity with this environment, immediately can put it in context with respect to the genetic environment and with respect to the exploration implications. You cannot do that with the simplified figure. You cannot do that with this figure. Silicification, argillic alteration, and advanced argillic alteration, for those of you, again, who are familiar with epithermal deposits, this would very likely be interpreted right away as a high sulfidation epithermal deposit with a zoning typical of a zoning of a high sulfidation, and that's not the case. This is not a high sulfidation deposit, okay? So that is one of the lessons. Use the mineralogy, document the mineralogy, because the same minerals, especially in this environment, can form in different settings. So what are we talking about? Let's go to basics. The definition of advanced argillic alteration is an advanced hydrolytic alteration. We are talking about hydrothermal alteration of the entire rock, but particularly of feldspars, for example, and other components of the rock-forming minerals of the rock and the matrix. So it was defined in the 1960s by Julian Hemley, and in particular Julian Hemley, who happened to be a graduate of the university I'm teaching now, the University of Texas at El Paso. It was then called the El Paso Western Texas Mining and Engineering or Metallurgy School. So it's an alteration group that includes aluminosilicates like kaolinite, dikite, halloysite, pyrophyllite, plus alunite, diaspore, andalusite, suniite, and topaz. Again, minerals formed from advanced hydrolytic alteration, in particularly of feldspar. Now, some minerals here are key, like alunite, and we'll see that later. So many of you are familiar with this graphic that shows the mineral alteration minerals associated with epithermal deposits, grouped by assemblages formed under acidic conditions, and these are exactly the same, essentially the same minerals, neutral pH conditions or alkaline conditions. And we know that these are very important, these assemblages of minerals form are very important for exploration to know when we are closer or farther from the ore body. I should say that this is not really, we shouldn't call these assemblages in the sense, in the traditional sense of minerals that are in equilibrium. These assemblages are not in equilibrium, so perhaps it's better to call them a mineral association or a family of minerals, because they are rarely in equilibrium, all of them. What does it look like? What does advanced argillic alteration look like? And that was the purpose of this painting by Thomas Moran, The Grand Canyon of Yellowstone. Now, this painting has a huge significance because this fellow, this painter, Thomas Moran, accompanied the expedition to visit Yellowstone in the late 1900s, and his paintings attracted much attention and were critical to make this the first national park in the US, and of course the first national park in the world, and something that has been extremely good for humanity around the world. So let's review again the minerals and chemical component involved. Again, alunite is a hydrated aluminum sulfate with potassium or sodium, or sulfate phosphates, where we have sulfate as well as phosphate, and then we have divalent cations like calcium, barium, strontium. Then the typical aluminum silicates, kaolinite, dikite, halloysite, all of them the same formula, different temperatures, form at different temperatures. Dominantly pyrophyllite, andalusite, diaspore, sunniite. Now we have chlorine, fluorine, and topaz. So all of these are ions, whether cations or anions, that are in solution looking for the mineral that will be in equilibrium in these conditions. And these conditions are typically that low pH, about 2 to always less than 5, to about 2. But they can go down to even less than 1 or 1, which is an environment where we form what is called the residual quartz or rocky silica in other places of the world. And Meyer and Hemley, they didn't include residual quartz as an advanced argillic alteration originally, but as kind of a silicic alteration, in reality is the extreme advanced argillic alteration. It forms at shallow depths, less than 1.5 kilometers, maybe even 2 kilometers in some strange cases, as you will see. What is the economic significance of advanced argillic alteration? Well, it is directly or indirectly associated with many, many economic mineral deposits and many metals. So in this figure, I show porphyries and porphyry copper deposits and epithermal deposits around the world. Obviously, in this case, connected to volcanic arcs. And I don't think I exaggerate if I say that a good half of these deposits around the world, or more than half, have an association, show minerals group under the advanced argillic association term. And obviously, within the porphyry, we're talking about the main source of copper, rhenium, osmium, molybdenum for society. With epithermal deposits, as well as porphyry, we are talking about one of the major sources of gold, silver, zinc, including lead, less so, but tin, and even today, minerals that are classified as strategic minerals or critical minerals like indium, potentially germanium, etc. Now, advanced argillic alteration is associated with this metal concentration, is also associated with key concentrations of minerals key to society, like sulfur, has been mined for sulfur, has been mined, obviously not at the scale of bauxite, but for alumina, for quartz, high quality quartz, for kaolin. Many of the largest kaolin mines are secondary advanced argillic alteration form under supergene conditions. And you are going to allow me a somewhat of a tangent here, digression, alum. And I imagine this is of historical significance. I imagine not many people are familiar with the term alum. So alum, we are talking about aluminum salts with sulfate hydrated. It's not alunite, but it's very close to alunite. And this was an extremely important industry early in history. Why? And I mean, there's a whole book with the title, The Earliest Chemical Industry. It was extremely important in ancient, especially around the Mediterranean, for two reasons: to treat, soften, and preserve leather. 2,000 years ago, what you wanted to have were shoes and clothes, and that's what that was about it. So shoes needed to be treated, leather needed to be treated, and the name of a Roman shoemaker was an alutarius, from alum. And alunite, of course, comes from the same root. And to treat and dye textiles, especially this purple color. So in Roman times, the toga picta was worn only by the emperor or by generals who won in a battle. This color came from this. Maybe some of you saw this in a recent last year article, an excellent article in the SEG newsletter on the name porphyry, where it came from, and it was connected to this color and to this sea snail that gave the extracted the red color, the crimson color. Well, to be able to dye this crimson color and to keep it in the clothes, alum was key. And alum was mined, for example, at some point, city-states in Italy had all colonies in Turkey for mining alunite to produce alum. So the Tyrian purple, this color was the traditional color of power. And if you have any doubt, that was the color of power, not anymore today so much, but if you go to a traditional community, you can see, if you type American bishops in Google Images, you got it. It's clearly the color of power. Now, the other color of power was black, and that came later in the in the 16th century, and that's another story, why that became a color of power. Also died with the use of alums. So alum is not anymore important. We make it synthetically today, and we have synthetic dyes, but it was extremely important early on. So, and again, advanced argillic zones were the source of much of the alum mining in the past. I'll come back to that in a second at the end with the gold mine in Spain. So let's look at the geological significance of the environments of formation of advanced argillic alteration. So we have 5 environments. Many of you will be familiar with 3. I'm going to add 2 more. So the first one is one of the most well-known, is the condensation of magmatic vapor, where SO2 and HCl from magmatic volatiles, again, we are talking about components, chemical components that are derived and exsolved from a cooling and crystallizing magma chamber at depth. So water, CO2, SO2, H2S, HCl, and metals. So the SO2 and HCl, condensation into groundwaters and into itself, the steam, the magmatic steam, produces a very acid environment, and that is a high sulfidation associated with high sulfidation deposits. Another one is the cooling of a high temperature white mica stable fluid. That is a little deeper. Third is geothermal vapor with CO2 that condenses or is absorbed in groundwaters below the water table and forms carbonic acid. Fourth, the same geothermal vapor, now SO2, H2S, excuse me, hydrogen sulfide, is oxidized by atmospheric oxygen above the water table, and this also produces an acid environment. And finally, the weathering and oxidation of fine-grained sulfides, typically pyrite, can form also an environment with sulfuric acid and alteration minerals, in this case of low temperature, secondary origin, we call. So these are the 5 environments. Now, from now on, the rest of the talk is going to be about looking at each one of these environments in more detail, looking at active equivalents where we can to help us understand them, and or deposit equivalents where we can understand exploration implications. So before I do that, I want to go to we're talking about magmatic hydrothermal systems, and these are these type of systems are best illustrated by Dick Silito's a classic diagram in the 2010 paper of the porphyry copper system. So this figure from his paper shows the continuum of alteration, of hydrothermal alteration in different colors, from sodic calcic at depth within the porphyry environment, closer to the magma chamber, then potassic alteration, we are talking about K-feldspar or biotite, second hydrothermal, then chloride sericite, sericitic, quartz pyrophyllite, and then these yellow colors. Okay, so let's look at this same section. Now, let's highlight the ore bodies, the mineralization, the different types of ore bodies that can happen in this schematically. Again, this is an extremely schematic figure to combine, to illustrate this environment of alteration and mineralization. So we have porphyry, if we have the right lithology, we may have a skarn or a carbonate replacement, or farther away, we may have a sediment-hosted disseminated deposit. And above, in the upper 1.5 to 2 kilometers, we have what we call, of course, the epithermal environment, and we can have different types of epithermal deposits. So let's look at these 5 environments of advanced argillic alteration, where we can have advanced argillic alteration minerals. The first one is this one at the base of and we call all of these, we follow the Silito's term, we call all of these the lithocap, this alteration envelope above a magma chamber that is degassing. So we have the first one is the cooling of magmatic hydrothermal fluid, white mica to pyrophyllite. Then we have hypogene acid sulfate chloride surrounding high sulfidation deposits. Then we have a steam-heated acid sulfate above the water table. Steam-heated CO2 rich typically below the water, typically on the margins of the upwelling geothermal system. And then we can have supergene, oxidation of sulfides. We can have it here, or we can have it in any system that has a fine grain, especially fine grain sulfides, or sulfides in general, like volcanogenic massive sulfides and other types of environments that you will see. And I'm going to simplify those 5 environments with formulas, chemical formulas, because each one is associated schematically, again, and making a generalization, is associated with a chemical reaction or a chemical component. So the first one, the highest temperature that leads to the formation of pyrophyllite, it is the reaction of muscovite with quartz as it cools, the fluid cools. Second one, condensation of magmatic SO2, here forms sulfuric acid and HCl, then the sulfuric acid and HCl dissociate and they form very acid conditions, and we have the widest assemblage of the advanced argillic alteration assemblage. Look that there is pyrophyllite here and there is pyrophyllite here. Another one is kaolinite form from carbonic acid, less acid conditions, and this is again CO2 absorbed into groundwaters below the water table. And here we have kaolinite here and kaolinite here. Or steam heated, where we have H2S oxidized by atmospheric oxygen in the vadose zone, forms sulfuric acid. And again, we have kaolinite, 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 alunite and alunite here. And finally, oxidation, supergene oxidation, weathering, oxidation of sulfides. Those two environments have a very strong bacterial involvement. So we have an inorganic chemical formula here, but in reality, they are mediated by bacteria hugely. So here we have again alunite and kaolinite. So it's important to understand, as I showed earlier, they belong in different places, especially with respect to our deposits. So let's look at the 5 environments in more detail. First of all, the higher temperature cooling of a white mica to pyrophyllite. So above a porphyry system, and is this assemblage that Silito highlights here, quartz pyrophyllite. We have always known, or we have observed, not known, but observed for many years that there is a kind of pyrophyllite-rich zone between the porphyry environment and the epithermal environment. And interestingly, in many systems, this pyrophyllite-rich zone, transitional to sericitic alteration, to white mica alteration, is barren. But as we keep learning, as we study more and more systems, actually there was recently a paper in economic geology on the Onto deposit in Discovery in Indonesia, where it looks like this pyrophyllite, quartz pyrophyllite zone is actually mineralized, heavily mineralized. So the minerals here, we have muscovite, pyrophyllite, diaspore, and allusite. That's a key mineral also found in other systems, a few systems around the world. Pyrophyllite, diaspore, muscovite, and allusite. Very often we find this nodular, patchy, wormy replacement texture that some of you would have heard in the porphyry environment or in the roots of high sulfidation or lithocaps. Very distinctive. Let's look at an example. I cannot show an active example because it's too deep for us to have, and we don't have evidence from an active system, but let's look at fossil systems. Let's look at El Salvador. This is a photograph by, from Jeff Hedenquist, a slide. So we have a muscovite alteration. The El Salvador porphyry is underground mine, and at the surface you can see a large muscovite alteration area with a pyrophyllite zone, which a pyrophyllite is, and this is a plan view, pyrophyllite is really an overprint. So this is the orange hatcher pattern for pyrophyllite overprint over a blue color for muscovite. And the porphyry copper ore body, in this case, this is the outline of the porphyry 400 or 500 meters below the surface. Still, we are within the muscovite zone, within what white mica zone and pyrophyllite overprint. And what are we looking at? Again, this reaction here. So from the porphyry, from high temperatures, we have K feldspar. We go to K feldspar to muscovite stability as the fluid cools, and then eventually it may go to pyrophyllite stability. So we are talking about this environment here. And that is, it can be seen with here where you see muscovite in a clear color in the SEM image, a backscattered electron image, replaced, overprinted by pyrophyllite as the reaction goes ahead. Now, this environment has a slightly lower, less acid pH than this other environment, which is the hypogene vapor condensation, which is the one we'll look at next. So this environment, hypogene magmatic vapor condensation, all of you are familiar with because it's the typical alteration host and associated with what we call high sulfidation epithermal deposits. So we have water, SO2, HCl being released from a degassing magmatic chamber, and at certain temperatures, starting between 300 and 400 degrees, SO2 starts reacting with water and produces sulfuric acid and H2S. This is a disproportionation reaction, and then this sulfuric acid and HCl directly from the magma, if it has not been buffered at depth, they start to dissociate and produce extremely acid conditions to the point that the pH can be below 1, and all these minerals, kaolinite, alunite, dikite, they are soluble at that pH, and they produce what we call a residual quartz residue, which very often is mineralized with gold, copper, silver in what we call, again, high sulfidation deposits. So this is a halo, this alteration, this color in orange, halo to high sulfidation mineralization. So let's look at this video. Some of you in the audience have been here. This is a hot spring in Japan, in Akita Prefecture, where I used to teach until a year ago. You can see all that boiling water coming out of the ground, no water above, advanced argillic alteration above, all these white colors. But you see there is no hot water coming out of the ground above. So all of that stream is coming out at this hot spring, and this is not the usual hot spring. This is a very unusual hot spring. In fact, this is called Obuke hot spring in Tamagawa geothermal area, and this hot spring produces almost 9,000 liters per hour. Excuse me, 9,000 liters per minute at a pH of 1, close to 1, boiling, 98 degrees. This is a 700 meter elevation. So we are talking about 9,000 liters per minute of extremely acid fluid at boiling temperatures, 30% of which is magmatic water, condensed. So this is a very, very special type of geothermal fluid. This is the one I was showing here. This is this fluid here. So this is forming a region of baggy silica at depth. Okay, let's look at another active environment where we can see this easier. This is in an island. This is also Jeff slide. This is an island in southern Japan, in the south of the island of Kyushu. It's called Satsumaibojima. We have high temperature magmatic vapors with very high HCl and SO2 content. And this alteration produced from these fluids produce this extremely silica-rich residue that was mined for silica flux. And here the concentration of metals is very, very low because we are talking about low pressure vapors, condensation of low pressure vapors. But around the island of Satsumaibojima, we have the same type of very acid springs with essentially dissolved rock that produce a precipitate of alumina, iron hydroxides, aluminum hydroxides, and other elements as they reach the cold water of the Pacific Ocean. So this is not what we see at Satsumaibojima because we cannot see it at the heart, but this is what we see in high sulfidation deposits, the kind of rock that would be produced at the heart of this volcano. Baggy silica, here, this is from the Summitville deposit in Colorado. Originally, this was a rock with it's a dome with large orthoclase crystals. In this case, the orthoclase, the feldspar is altered to kaolinite dikite in white, Here is altered to alunite, it's pinkish and crystalline, entirely altered to alunite, and here is completely dissolved because of the pH. So here we have a pH less than 1, here we have slightly higher pH, 1 to 2, here we have a slightly higher pH. It's this figure here. So on the x-axis, we are looking at pH, and at the residual quartz, we have an extremely low pH, alunite, kaolinite, dikite, moscovite, K-feldspar. And this is the classic zoning of epithermal, high sulfidation epithermal deposits. And we know that mineralization is typically within their residual quartz, the baggy silica zone, or extending into the advanced argillic alteration halo with alunite, kaolinite, but concentrated here. And this alunite here, again, hydrated sulfate, potassium aluminum sulfate, typically or commonly is platy, tabular, looks like barite. It will be different to other alunite form in other environments. This photograph here, for example, shows a direct transition between residual quartz and kaolinite dikite. There is no alunite here, or very, very small amount of alunite. So we are looking about this transition here. Let's look at deposit. That was the active environment. Let's look at ore deposit. So this is the El Southall gold silver deposit in Mexico. This is a photograph in the 1990s. Before, this is during exploration. So we are looking at what in the Soviet literature they would call a secondary silica massif, a secondary quartzite massif. This is a baggy silica, residual silica zone. Actually, this was little baggy because the rock was had a very fine grain igneous rock, and it was porous, but didn't look like the typical baggy texture because it's really a texture baggy, but it's the same residual silica rock, surrounded by orange color advanced argillic. Now, I'm doing here the classic do as I say and not as I do. I'm showing orange advanced argillic. I'm making that simplification. Today I say don't do that. This was a figure from an effort by Jeff and I looking at high sulfidation silver deposits around the world, comparing, and obviously we had to simplify and we had to use simplified colors. But I would say don't use that, use the minerals, the assemblage that is there. So what happened to Southall? Well, this is a photograph some 6 years ago, and you can see that what used to be here is gone. So that was the gold deposit, strictly the silicic core, very steep, very hard silicic core that was mineralized, this ore body here. And obviously this had very important, this observation, the silicic, very important exploration implications. You want to sample in the steepest rock, you want to sample very high density where you have silica, you don't need to sample as higher density where you have kaolinite or propylitic alteration, if you know you are in this environment. Number 3, steam-heated alteration, formed by oxidation of hydrogen sulfide above the water table in the Vado zone, oxygen-rich zone, very oxidized, atmospheric oxygen, water and is not saturated with water, but there is water and there is also oxygen. The pH in this zone is not as low as in the previous example, 2 to 3. Temperatures are around boiling because that's the temperature, the maximum temperature here, but you can have higher temperature geothermal vapor coming from the deeper geothermal fluid to the surface. Simplified reaction, again, there is bacterial involvement. Minerals, we don't have pyrophyllite here, but we have kaolinite, we don't have dikite, that's higher temperature. We have kaolinite, alunite, and then we have lower temperature forms of silica, like opal, chalcedony. Very often there is a blanket of silicification below the steam heated zone, which is colored here in orange, from silica that is transported from deep within the geothermal system, as well as silica remobilized from within the steam heated zone. And that forms a silica a table, an opaline or massive opaline or chalcedonic blanket. What else? Native sulfur, very common here. So this probably this reminds you, at least here, we are talking about opal, alunite, native sulfur, kaolinite. This is a typical appearance of this steam heated alteration. Very important because from an exploration point of view, if as we know, this hydrogen sulfide is released by boiling of the geothermal fluid dominantly, and that boiling would be under normal conditions directly below the steam heated zone, because that's the shortest path for this steam, geothermal steam, to get to the surface. So it's a better path to ore than, for example, a silica sinter, which may be farther away from the boiling zone at depth. So this is a video from Yellowstone National Park. This is a classic steam heated environment. Look that we don't see here waters, a hot spring venting out of the ground and going downstream. We see a pond of water, rainwater, ponded here, through which steam as well as CO2 is bubbling through. So this is not necessarily at 100 degrees Celsius, because this is the steam is higher, bubbling through it, and it's heating. It's a steam heated environment. So it's heating this ponded water. And this was just recently, this was in the news 1 week ago. Boiling chickens in Yellowstone hot springs is illegal, apart from very stupid thing, because you can die. This is the typical or the extreme view of this environment, steam heated, when it reaches the surface, the typical mud volcanoes. You can see the very strong white color, kaolinite rich. That is very common. So bubbling, again, CO2 and steam bubbling through and producing an acid environment that results in alteration in this environment near the surface. Let's look at this type of rocks in ore deposit. So here is the La Coipa gold silver district in Chile. We are looking from above. We are looking at a large area of alteration. This rock unit is younger. This rock unit is younger too. The here is covering this alter zone. Here is intruding through it. And we see here the mine plant. There is a large pit here, Ladera Farellón, sulfides, oxidized sulfides above. There is another open pit here, it's called Coipa Norte. And you can see very well a very white zone of alteration, which these are remnants of the steam heated alteration that goes close to the surface. So there is a lot here, much less here. Underneath this is called Cancan, and there are underground high angle load gold veins, and then Ladera Farellón with a little bit of steam heated above. Let's go to La Coipa Norte, this ore body. So this is what you see. The white, porous, brittle, alunite, kaolinite dominant, alunite, native sulfur, opal, chalcedony rich zone. And below here is the primary ore, is a high sulfidation deposit. In this case, it's a silver-rich deposit. It's the residual quartz. You can see here in feldspar, altered to alunite. The feldspar is completely dissolved here. So quartz alunite, vaggy quartz. And then these pores were filled with native sulfur, which were more likely coming at a lower temperature, coming from the steam heated zone above. This is a sample from that steam heated zone above. White, porous rock consisting of opal, alunite, kaolinite, as well as native sulfur. This is the type of alteration that was shown at here, that was meant to be shown at here, and was originally shown properly. So if you go around the corner in this district in La Coipa, there is an area, this is about 30 square kilometers of steam heated alteration with native sulfur ore workings, with a massive opaline horizon. You can see it here. You can see the remnants here. So here we have the steam heated profile, beautifully preserved with a massive opal horizon kaolinite native sulfur. And in one of these, not in this one, but one to the north, a new discovery was found underneath this steam heated zone with the white colors. But in this case, it's not a high sulfidation type ore body. It's an intermediate sulfidation type ore body where we have illite also as part of the alteration. This is also a silver-rich ore body. It's called Puren, North Puren. And they keep finding at the La Coipa district deposits below this steam heated, covered by this steam heated alteration. Let's look at another one. This is in Nevada. Used to be called the Sulphur district in Nevada. Why? Because it was a sulfur mining area in the late 19th century, the 1800s. So they used to mine sulfur, these structures, mercury. So these are all samples this is from Mindat, sulfur, mercury, clays, kaolinite, the white colors. What do we see here? This is a photo in the 1980s. So we see here in the back, sinter, silica sinter, where, well, guess where the gold silver mine has been discovered later? Underneath the sinter or underneath the steam heat alteration? So this is the view today, right underneath here, these structures. You can see the structures here going north-south, and these are these same structures here in the Crowfoot-Lewis South Pit. This is an elongated open pit because they were mining a high grade or higher grade gold structure. And this structure was feeding, like this one, within propylitic alteration rock, feeding a steam heated zone at the surface. And this, if you want to read more about it, there's a fantastic paper by Ebert and Rye in 1992, where you see, or the 1990s, and where they describe a massive opal horizon below this steam heated profile, consisting of friable silica, opal, alunite, kaolinite, jarosite, hematite, cinnabar. Actually, during the 1980s, this was the top mercury producer in the United States, believe it or not. Mercury entirely from within the steam heated zone, a very, very thick steam heated zone. And I'm going to go to what is probably the best example of a steam heated alteration above an epithermal system in the world. This is Pascua Lama. Pascua, if we do a cross section, this is looking from Argentina towards Chile, from the east to the west. And these very bright colors, you can see all the drill roads. They are drilling, looking for, measuring the ore body, which is at depth, but these white colors are indicative. It's not just snow, it's the kaolinite. So this is a cross section perpendicular to this ridge. Quartz alunite, kaolinite, decay pyrophyllite from condensation of magmatic vapors in light orange. In red, in light red is the residual quartz. In dark is the gold, as well as silver. It's very similar, it's slightly offset, but mostly associated with this horizon of residual quartz, and all of it covered by a low-grade to barren quartz kaolinite zone of a steam-heated origin. It's about almost 200 meters thick here. This is a phenomenal example, very well documented in this paper by, I forgot her first name, sorry, Chouinard. Okay, let's go to the fourth type of environment, steam heated, where we have a geothermal vapor with CO2 that condenses in the groundwaters and produces carbonic acid, CO2 plus water, carbonic acid. And this typically happens on the margins. This is an environment, frankly, I am less familiar with. This is an environment that Jeff knows better from geothermal systems in New Zealand, active geothermal systems in New Zealand. But it's very well illustrated in this classic figure, this CO2 rich on the margins of the geothermal upwelling zone. So we have the steam heated sulfide rich above the water table and CO2 rich below the water table on the margins. And this forms pHs of say 4, 4.5, doesn't get as low as 2 or 3. And we can only get kaolinite, lower temperature, as well as only this mineral. from the acid alteration mineral. But it's important because we can have the illite kaolinite assemblage, and it's important to interpret it properly. So let's go to New Zealand. Let's go to Broadlands geothermal system. The venting of geothermal power drill holes for geothermal power. And let's look at the cross section across Broadlands. This is a cross section, isotherms, the deep upflow, the isotherms clearly showing that here, deep upflow, boiling and vapor loss. This releases, this vapor loss releases H2S as well as CO2. The H2S oxidizes near the surface, a steam heated zone. We have these mud pools, kaolinite pools, classic steam heated alteration. On the margins, we have this CO2 in color, in yellow, they form kaolinite, this carbonic acid forming kaolinite on the margins. And in fact, in one drill hole, even in this number 6 drill hole, they got the fluid venting just like if it was a soda, a Coca-Cola or a beer, CO2 rich froth coming out of the ground. So we see siderite, carbonate, kaolinite on the margins of the upwelling zone. Where is the ore? Where is more likely going to be the ore zone? Here. So it's very important to keep this in mind. First of all, interpret the kaolinite properly. It's not the kaolinite that is associated with the high sulfidation deposit. Second, keep in mind the potential location. And this is also from Jeff, is a structure, a vein in Siberia, Kupol, a low sulfidation vein with typical low sulfidation textures. It's a long vein. I'm going to look at the long section here and the alteration minerals. So this color, the pink color, and a cross section here, we have illite kaolinite. So this kaolinite here is very common in intermediate sulfidation systems. It's very different from the kaolinite, alunite, and residual quartz of high sulfidation systems. It's very important to make that distinction for exploration. It's not so critical, it's just common sense, but for exploration, it's important to make that distinction because the zoning, for example, from the ore, from the high-grade vein, the zoning here is, you can see it in this image, green colors, chlorite, illite chlorite, chlorite, illite chlorite, illite kaolinite, illite smectite. This zoning is very different to the one I showed earlier for a high sulfidation deposit when we go from in proximal alteration was residual quartz, then we have quartz alunite, quartz dikite, clays, eventually propylitic. So here is the opposite. The higher temperature and closest to mineralization is chlorite illite. Finally, supergene weathering sulfide oxidation. Above the water table by supergene oxidation of pyritic rocks. A strong bacterial involvement. Now we have kaolinite and halloysite, the low temperature form of kaolinite. Very different crystal type. It's tubes instead of plates. But we still have alunite. We may have jarosite, very common, hydrous iron oxides. And this is a very good example of one of these supergene weathering zone. This is from a porphyry copper in Arizona, from the Santa Rita, the Chino mine, Santa Rita copper deposit in New Mexico. This is a photo by Ryan Mathur. So we can see very nicely the leach zone. This is the kaolinite clay rich zone, but also leach from copper, any primary copper, then secondary oxide copper minerals, and then secondary copper sulfide zone as the fluids leaching copper from this supergene horizon react with the sulfide, with the primary sulfides, and they produce secondary sulfides like chalcocite, cobellite, etc. Of course, this is a key factor to make porphyry coppers that are subeconomic, to make them economic. And it's a key factor in porphyry coppers in Chile, as well as in Arizona, and other areas where this weathering occur. So this is a schematic diagram of how that happened, pyrite-rich rock, water table, and we get meteoric waters, and simply this is the acid environment forming above. The alunite in this environment often, if not always exclusively, but often has a different crystal habit to the one at high temperature in condensation of magmatic vapor. Is pseudo-cubic, like these ones, or orthorhombic, with nearly cubic angles. So these are from 2 deposits in Spain. I'll show you right away where they come from to make more sense. So this is from Rodalquilar. This is this type of alunite from Rodalquilar. Where is the alunite, the secondary alunite, and the primary alunite here? So this is an open pit mining residual quartz within an envelope of quartz alunite, pyrophilite, dikite, halloysite, quartz alunite, dikite, kaolinite of hypogene origin. The structures, the high-grade structures are here. This is the primary alunite. The age was 11 million years. These white patches here are supergene, as well as all the iron oxides are product of supergene, secondary alteration. The age is 3 to 4 million years. So 7 million year difference between the hypogene event and the weathering supergene event. This is the alunite. This is the supergene alunite. The hypogene alunite is classic, pinkish, clear, crystalline, platy. The supergene alunite forms these masses, powdery or porcelaneous masses, chalky masses of alunite, jarosite, kaolinite. And in fact, at Rodalquilar, it was very, very pure, and they mined it, believe it or not, for centuries before they mined gold here. They were mining alunite for alum. They were mining it secretly because at that time, the Pope in Rome had a complete monopoly on production of alum, mining of alunite for alum from the Tolfa deposits in Italy. But in this corner of Spain, they were mining alunite for alum illegally, if you will. So again, 3 centuries earlier, they mined alunite and they didn't know there was gold in the same place. This alunite may form in an environment that has nothing to do with hydrothermal activity. So this is a pyrite-bearing black shale of Paleozoic age in the center, in the middle of Spain. And these are nodules of pure kaolinite alunite formed in the Miocene from weathering of this pyrite, fine-grained pyrite from organic matter-rich black shales, together with the gossam on top, typical, the gossam layer here. And they were mining this for clays, as well as trying to mine for alumina, measuring it. And this is the same type of alunite, powdery, porcelaneous, chalky. Finally, supergene weathering is, again, has a very, may have a very positive economic impact. So one way is releasing gold from gold in pyrite, whether it's in a pyrite structure or as in small inclusions in pyrite, but the oxidation of pyrite will release gold. This is from Rodalquilar, is what they used to call the red clays, the highest grade gold ore. And it can also do the same thing from copper, release copper from copper sulfides and produce secondary copper minerals, which can be leached at lower cutoff grades by solvent destruction electrowinning. So this drops in addition to being able to do a secondary enrichment, it can lower mining costs by lowering the cutoff and make a deposit economic, which otherwise wouldn't be. So to finalize, to end the talk, I'm summarizing the 5 environments again and their approximate distinct temperatures, as well as distinct chemical components for the 5 environments of acid alteration. Again, these are not only the 5 environments, there are more in the geological picture, but these are 5 that apply to this type of deposits. And again, where they schematically, where they belong with respect to these ore bodies. This zone red, excuse me. Orange, quartz alunite, quartz kaolinite, farther away, lighter orange. Green, steam heated. yellow, steam-heated CO2 rich, illite kaolinite, and finally, supergene can happen anywhere. Now imagine this environment here, this uppermost 200-300 meters, here especially. You can have 1, 2, 3, and 4, the supergene, types of kaolinite or alunite. One is primary, the other is clearly secondary. This is also primary, this is primary, but it's descending. Some are ascending, some form from descending water. So this environment is extremely complex. And this is the kind of situation we will find often when studying epithermal deposits, like the study at Pascualama, where she encountered this kind of very difficult transition, and it's very difficult to say what belongs to what. It's a very difficult solution, but it's a very natural situation to have all this overprinting and complicated environment. We have the same overprinting here between two settings. And with that, I will finish with practical recommendations. First, distinguish the environment of formation based on the mineral assemblies, the textures, mineralogy, morphology of the alteration zone. Most important, map it. Integrate those observations with lithology, with the structures, which are very often the conduits. Keep in mind that we are talking about hydrothermal deposits, and lithology and structure control permeability. So we want to keep always these observations in context within the paleopermeability. So that allows us to interpret the location relative to the potential for mineralization and determine all of these aspects and how they are relevant to exploration depending on the stage of assessment. Are we looking at the earlier stage or later stage? Finally, the basic recommendation, focus on mineralogy and avoid names. Use the white porous rock with opal kaolinite alunite versus advanced argillic alteration. So let's go to the real thing, to Yellowstone River. This is a photo of Yellowstone, the Grand Canyon of the Yellowstone. Here we have a phenomenal steam-heated alteration, advanced argillic alteration zone. I don't know the origin, frankly, I don't know the origin. I don't know if it has been studied in detail. But if I was in exploration and I encounter something like this, having this framework of understanding would help me where to start, what to do. For example, I would want to know if this is kaolinite of a steam-heated origin, if this tabular harder rock, is that an ignimbrite or a layer of igneous rock, a volcanic rock that is less altered, or is it a vaggisilica horizon, a residual quartz horizon? Is this dark? Are these dark outcrops here or here? Are they dark because they have sulfides? I forgot to mention, pyrite is always is present almost everywhere, but especially in the type of alteration that is associated with the porphyry and the high sulfidation deposit. So I would want to know right away if this is dark, is associated with residual quartz and pyrite, or is just a weakly weathered, maybe secondary weathering of a volcanic rock. It gives you again guidelines on to where to start and what working models to use for exploration. And with that, I will finish. I'll turn on the video, and Filipa, if you want, I'm happy to answer questions.
Okay, thank you very much, Antonio. Actually, I'm speechless. It's amazing talk. And I really appreciate all the educative examples where you use field photos that explain all the points that you are mentioned. And I was looking to this last slide, and fortunately I was in Yellowstone 2 years ago. And now for sure, I will look to my photos with another perspective and thinking about how and what is this. So the first question from Michael is, Antonio, in the field, how do you visually distinguish between supergene alunite and alunite directly related to the hydrothermal alteration system?
Okay, so as I said in the last slide here, it's important to gather a variety of evidence. So there is not going to be one exclusive, one diagnostic observation. But it's important to gather, to aim to gather information on the mineral assemblage, on textures, morphology, at least those three, and the morphology extremely important. So what are we talking about? Mineral assemblage. Well, if you have alunite and jarosite, or alunite and pyrite, that's a different thing. So if it's supergene, it's very likely you are going to have alunite and jarosite and kaolinite, and maybe you can look at the kaolinite and see if it's halloysite, what you get in XRD, but then it's halloysite when you look at it in the SEM. So the assemblage is important, and I gave in the talk, we gave a series of assemblages, each one. Now I tell you, at Rodalquilar, when I did my PhD at Rodalquilar in the Paleozoic a long time ago, it took me a long time to identify that supergene alunite, a long time, because they overprint each other. And in the end, we were able to separate kaolinite of supergene origin from kaolinite of advanced argillic of hypogene origin, and do isotopes on them, and be able to prove that the water associated with the supergene kaolinite was rainwater, groundwater, and the water associated with the hypogene alunite was magmatic steam. So there is nothing that you can do immediately, right away, and tell you this is supergene, but the combination. Another, and time, and think about it. Another morphology, is it tabular? Does it look like it's clearly associated with the uppermost meters of cross-cutting structures that are allow permeability going down? The supergene fluid is going down. So do you see that it's very, very strong on the upper meters and then it dies down? That would be an argument for supergene. Iron hydroxides, are there iron hydroxides or not? Is there another one that is more academic, but is sulfur isotopes? So there is a whole paper, 1992, by Bob Rye et al. On the stable isotope systematics of alunite. And you can distinguish very well with sulfur isotopes, alunite form in high temperature environment versus alunite form in the steam heated or supergene environment. And the high temperature environment from magmatic gases is very heavy, sulfur isotopes. So there is a variety, there is a framework of observations, not just one.
Thanks, Antonio. So there was a question on alunite, but maybe we can extend a bit on the kaolinite. So I don't know if on the field you can recognize as alunite different type of kaolinite. And here I have a question from G.L. Gutierrez, who is asking if it's possible to distinguish different types of kaolinite using infrared spectra or portable devices.
Okay, so I'm going to comment on a couple of things. I have some pet issues, okay? I'm going to take advantage of this one, of this opportunity. For those of you who are always interested in finding ways to identify a mineral based on a new technique like portable spectrometry or remote sensing, please start thinking more in terms of the field. More field, more observations in the field, more observations on morphology, on mapping, are going to give you the answer much more readily than any remote sensing or remote tool. Okay, so maybe I am an old guy here, but manage our interest in identifying these environments on the basis of something that requires little work and just using a computer. Go to the field, map, document, and you will find the answer. So when it comes to, it's the truth, and you will be in the field during days and weeks not understanding.
No, I do agree, but then you showed that there are areas where everything overlaps, and then it gets a bit...
Exactly. So imagine if nature is so complicated to where everything overlaps, if that is the case, how can any tool tell you the difference? No. So it's in those cases precisely where there is overlapping, where mapping is even more important. Why? Because spending time in the field or logging core allows you to try to separate the end members. If there is overprinting, the thing you need to do is identify the end members that overprint. If there is grays, it's because there is black and there is white. So you want to know where is the black and where is the white. You are looking at gray, shades of gray. But to say in which direction do I go to the end member A, say hypogene, versus the end member B, say supergene or steam-heated, is through mapping and through documenting as carefully as you can that will tell you which way to go. And that meaning I have to go deeper. You saw that example at Pascua. You go deeper and you go to magmatic hydrothermal alteration. You go shallower and you go to steam-heated alteration. And you may need to go deeper, a lot deeper. I remember when I was at Rodalquilar, there was a brief paper, a very young student, describing the alteration zoning of the Rodalquilar of sericitic to advanced argillic to near surface argillic alteration, intermediate argillic, in an outcrop on the roadside. I'm talking about a few meters. In reality, that zoning is over 1 kilometer. So again, mapping and logging core and spending time looking at the rocks will tell you, am I looking at the decimeter scale or I'm looking at hundreds of meter scale or a kilometer scale? Which way do I need to go? And eventually you will find the answer. It will take time. Spectral tools are phenomenal. They are a phenomenal complement. They can help you distinguish minerals that are very hard or otherwise impossible to distinguish except with XRD, pyrophyllite from kaolinite, possibly from alunite even. So they are a fantastic complement to the previous. I don't trust so much some of the claims by people in the spectral community business that you can distinguish high temperature alunite from low temperature alunite or high temperature illite from low temperature illite. I don't think the tools are always reliable enough to be able to say that only with that tool. So kaolinite from halloysite, frankly, I don't know if you can distinguish with infrared spectroscopy. I doubt it. But they are infrared tools critical to help you this with the mineral assemblage. The mineral assemblage is going to come from infrared tools, from X-ray diffraction, from visual observation, etc.
Mm-hmm. So yeah, so in the end, portable field spectrometers are field tools for mapping, says Anne Thompson.
Exactly, they are a field tool, just like any of the field tools, except that is phenomenal. I mean, we couldn't 20 years ago separate pyrophyllite from kaolinite except with XRD. I still recommend using as much as you can XRD. It's a phenomenal tool. But in the field, a portable infrared is a fantastic tool.
Nice. Yeah, there's a bit
and I understand you can distinguish well dikite, for example, from kaolinite, and being able to connect, for example, quartz dikite with ore versus kaolinite. Those are key observations to be able to make.
Okay. Thank you, Antonio. We have another question this time from the YouTube. Antonio, any comments on the presence of these hypogene mineral phases like alunite and pyrophyllite in relation to the system fertility?
Any comment on the presence of these minerals in relation to the system fertility?
Yes.
Okay. Yes, I think some of them are to some degree self-evident. So if you have a huge area of what looks like a steam-heated alteration. So let's look at the photograph here. Okay, I'm going to assume, and that's dangerous, assuming, but I'm going to assume this is not a silica, a residual quartz horizon. I'm going to assume this is a volcanic layer, if you will. I don't know if it's ignimbrite or a flow that is not altered enough to keep, it keeps some consistency. So I'm going to interpret this and these colors, this iron hydroxide, more as either supergene or steam heated alteration. Okay, if I go now to the field here and I find this indeed looks like a steam heated alteration, there is kaolinite, there is some native sulfur, there is opaline silica. This looks like a thick steam heated alteration zone. Well, that immediately is an indication of fertility because you have a geothermal system that is strong enough to produce this alteration. Well, where would the ore be? Below, beneath. We would be above because this is produced from geothermal, from gases released from a geothermal fluid. If, by contrast, this was residual quartz with alunite, kaolinite around it and dikite, of course, it's an indication of fertility because we are talking about the type of alteration that is associated with epithermal, high sulfidation epithermal deposits. So something important to keep in mind. This alteration may be a necessary condition because it shows that there was enough hydrothermal alteration. There was a magmatic hydrothermal system strong enough to produce a significant amount of hydrothermal alteration, but it's not necessarily a necessary condition. Excuse me, sufficient condition. Excuse me, I made a mistake. It's a necessary as an indication of hydrothermal activity, but not necessary, not sufficient. I go again. You may have this alteration and you don't have the mineralization. Why? We don't know in all cases, but we know that most volcanoes or many volcanoes have hydrothermal alteration. Few volcanoes will have an ore body in them. However, and I'm going to show you, I had this slide here, the lithocap. If you have a zone of alteration big enough, this is from the 2010 Silito paper. If you have a zone of alteration of the type we call lithocap, again, made by these minerals from a magmatic, from degassing of a magma chamber at depth, and is big enough, that is an immediate sign of fertility because you have a magmatic hydrothermal system that had enough water, enough fluids, and enough strength and time to form this wide body of alteration, this large body of alteration. So it has the potential to form mineralization. And that is what is happening today. Today we are drilling that paper, for example, on Onto deposit and many others. Today people are drilling through hundreds of meters of lithocap alteration to find a deposit below. So fertile, yes. Guaranteed an ore body, nothing is guaranteed.
Okay, thank you.
And let me, sorry, just one more factor. I was part of an exploration project with Placer Dome in the late 1990s in Indonesia called Tujuh Bukit. We explored for the epithermal. We explored for, I'm going to go to this slide quickly. We explored for this high sulfidation epithermal. We were not exploring for porphyry. We didn't want copper. It was too deep. Anyhow, we dropped gold price was very low. We dropped the property. 7 years later, another group came. Why did they come? Why did they like it, that property? Because they saw this orange alteration zone, this lithocap, that was very, very large. And they said, if we have this alteration and this have a very large lithocap, in this area, we better drill deep underneath. And they found immediately below a phenomenal porphyry copper. Again, this is, to you book it. There is a paper in economic geology by Rachel Harrison. You can read that. It's an excellent paper. And it's again, recognizing fertility. These lithocaps of a large enough dimension means highly fertile potential. Yeah, go ahead.
Okay. So we have a lot of questions, so I'm sorry if we are not reading your question. I have a question from Chao Yang, who is asking, do you have a geochronological consideration that the steam-heated system is following the high sulfidation related kaolinite, alunite as a continuous process or as a younger event? And usually how long it takes to form the whole steam-heated and high sulfidation related alunite kaolinite system?
Can you repeat the last question, the second half?
Usually how long does it take to form the whole steam-heated and high sulfidation related alunite kaolinite system? Just the timing of the formation.
Okay, so do we know if this steam-heated, the timing with respect to this hypogene acid sulfate chloride?
Yes.
And second, the length of time.
Mm-hmm.
Well, the simple answer is I don't know in detail, but I can say some informed, educated guess. So if we have this alteration, hypogene acid sulfate chloride alteration, it's very possible to have also alteration at the surface, steam heated. It's not possible, it's not just possible, it's very likely. Because these are magmatic hydrothermal fluids, and what do they want to do? They are volatile rich, they want to go up. So it may be a case where they are absorbed below the ground surface, or we see very little steam heated alteration, but there is a much larger magmatic hydrothermal system below. So it's a matter of permeability, but the timing, they should be happening at the same time. The same fluid that is ascending and is producing this alteration eventually reaches the surface, the same environment, really. But I am not willing to say, I mean, I cannot say it's post. What you can see is native sulfur, for example, at the La Coipa case, native sulfur filling the empty spaces in the residual quartz, in the baggy-silica. Well, that is clearly, there is a timing relationship there. You see the native sulfur coming after the leaching. So at least in part, these fluids were active at a later stage and they were descending into the residue of, into the residual quartz. But they are contemporaneous for the most part. Again, steam heated may be very, very minor manifestation because of the permeability conditions is absorbed underground. But I would imagine at some point you see something at the surface. And the second one was the timing. This is a very good question, or at least it's a good question and give me a good opportunity to make a point. So you see papers, you will read in papers that these epithermal deposits or even the porphyry form over millions of years. In another cases, you will see papers saying they can form in tens or hundreds of thousands of years, tens of thousands of years. So why do we say millions of years or tens of thousands of years? Well, each individual ore body in reality will likely form over a very short period of time. From what we know, it could be just tens of thousands of years, or maybe 100,000 years, 200,000 years. But this is a very dynamic environment. And there isn't just one intrusion and one magmatic hydrothermal event. There may be many associated with the magma chamber at depth. So here you have a magmatic a diatreme forming, and then you have intrusions, and you could have another one here, you could have another one here, and you could have another one here. And each one of these can have an ore body associated with them. So overall, a district like this one will produce mineralization over a few million years, connected to the same magma chamber, perhaps. But each individual ore body or deposit will likely form over a much shorter period of time. So if you go to Yanacocha, the large high sulfidation deposit in the world, the largest, the history of the Yanacocha district took a good 5 million years, from the very first deposit in the district to the very last deposit in the district. But each one of those deposits form much, much faster. And in fact, a good 70, 80% of the gold precipitated at Yanacocha was precipitated in a period, this is dated, this is a PhD by Tony Longo, and a paper in economic geology too, and it formed over a much shorter period of perhaps just 200, 300,000 years, 500,000 years.
Okay, thank you, Antonio. We have another question from Ivan Krumov. Do you want to unmute yourself and ask the question? I will read it. Do all these mineral assemblage related to acid alteration depend on the host rocks? And you have seen acid alteration developed in sedimentary or metamorphic rocks?
Yes, host rock is extremely important. Yes, I have seen them in metamorphic and sedimentary rocks in both cases. So obviously host rock is extremely important, the host lithology. If you have a host lithology that is felsic in nature, is made up of feldspar, it will be very happy to form alunite. There is aluminum there, there is potassium. If you have a host rock that is ultramafic, it will be a different matter. But it's a matter also of intensity of the processes. So it may eventually form the same minerals too, because there will be enough aluminum and sulfide. Obviously, it depends on all of this. The formation of this alteration depends on the source, on the fluids and the nature of the fluids. If you don't have sulfur-rich oxidized sulfur, SO2, it doesn't help forming alunite. It will definitely not form. It will form other advanced argillic alteration minerals. It will form kaolinite and pyrophyllite, but not alunite, for example. And then the lithology. And finally, yes, they can form associated with, they can form in metamorphic or sedimentary rocks. You have examples around the world. There is example, for example, a fantastic example in Peru called Quijirca system, where you have carbonate rocks altered to alunite quartz, dirty carbonates, and forming a high sulfidation ore body. In this case, the alteration is not massive like this one. It doesn't happen at huge volumes, but it happens in conduits within these carbonate rocks, carbonate host rock. And it's much more focused, but eventually these rocks also produce the same assemblage, alteration assemblage. And you have epithermal deposits with sedimentary host rock. There is one, Lagunas Norte in Peru, again, where 80% is hosted in sedimentary rocks. It's just that this is a volcanic setting, and volcanic rocks are very common in the shallow parts.
Thanks. We have reaction on the chat from what you said. Jeff is saying regarding the Yanacocha C. Longo et al. 2010, the deposits are distributed in the district over 12 kilometers, with most deposits associated with domes that individually extruded from 13 to 8 million years, related to a 8 to 10 kilometer deep evolving magma chamber that had intermittent injections of deeper magma. So yeah, just some comments.
I'm glad to see Jeff is there. He should.
Yeah. If you want to react,
on the microphone.
you can unmute yourself and participate to the discussion for sure. You're welcome. Yeah, so because are you going to publish about this work, Antonio? I think you said you will publish. It's something you.
Yes, we are working on it. We are working on it. I'm following. Jeff is leading, so we will get it one day, one of these days.
Listen to. Okay. Yeah, we have a few more questions. Maybe I can pick up one. Some are really broad. We have a question from Andrew. So he's asking if what is the potential for the formation of this type of alteration in submarine environment? I don't know if you can say something about that. How do you think the alteration mineral assemblage would vary? And thanks for the great talk.
That is an excellent question, and we make progress. Okay, so we have in the 1980s people started to classify epithermal deposits and bring the two types of deposits associated with different types of alteration. In the 1990s, we started to see submarine volcanogenic massive sulfide deposits as not just the mid-ocean ridge related, but also backart related, where it turns out that there is some gold or precious metals, and it turns out that you have exactly the same environment as magmatic hydrothermal sulfur rich oxidized sulfur, and you have exactly the same alunite and quartz and native sulfur. So many of these, and we are again in the, we continue to be learning, to learn. So that's a very interesting field, how much of what we are describing on land applies to submarine deposits. And more we see for shallower submarine systems in volcanic arcs, in submarine volcanic arcs, like the Tonga Kermadec arc. Again, we're not talking about reef zone. Now we are talking about submarine volcanic arcs. And the environment essentially looks the same. And last year they were drilling, deep drilling a system off the coast of New Zealand in the Tonga Kermadec arc, looking essentially for a porphyry type deposit. But we have the alunite, we have a kaolinite. There is a bunch of papers. I was involved in a couple of them in documenting the submarine alunite. It has more calcium, it looks like, but it's a magmatic hydrothermal environment, just the same. And it's the copper, silver, gold, lead, zinc mineralization, just the same. It's the volcanic arc in a submarine setting rather than in a on-land setting.
Okay. Thanks. Thanks, Antonio. Yeah, we've reached an hour and a half, so maybe we can slowly conclude on the topic. I don't know, something popped to my mind is like, now through time, there has been so many different classifications. Do you think it's gonna, I guess it's gonna evolve still, all these classifications to talk about porphyry and epithermal deposits? Do you think we will reach at some point some model where we will all talk about the same thing without changing names? And
well, it's a very interesting question. Thank you for asking me that. I am part of it, okay? I am not part of the names, but I am part of, I consider myself part of distributing these names and making them known to the wider community. And with, so my feeling is, look, of course, everything has to evolve. In some ways, we are just repeating what some people, very smart and very insightful people, said 100 years ago. So anyone with an interest on high sulfidation epithermal deposits, I recommend you to read Ramson papers in the first issue of Economic Geology on the deposit, the Goldfield deposit in Nevada. And essentially, everything he says is relevant today. He's talking about magmatic hydrothermal fluids, reaction with wall rock, how much fluid, how much groundwaters, what type of host lithology, and all that, and pulses of fluid, and all that, you end up with a deposit. And we have been evolving. So in the 1980s, we started classifying epithermal deposits into groups that help a lot. In the 1990s and the 2020 years ago, we started then in two settings, volcanotectonic settings, where you have the arc, extensional rift, and the volcanic arc. And you have the low sulfidation member versus the magmatic hydrothermal member, where you have high sulfidation, lithocaps, intermediate sulfidation, and porphyries, and the image I showed you earlier. Of course, it needs to evolve. It will evolve as we learn more, as we document more deposits, and as we think more about and improve the previous models. The only comment I will have for anyone is don't spend too much energy criticizing what was done before and saying all the models until now are wrong. Here I come with a new one. I'm saying this because I'm reading now and reviewing a paper that is exactly the starting point. Everything that was said before about high sulfidation deposits is nonsense. Well, don't do that. Just contribute. Be constructive. If we know what we know today because of what was done 100 years ago, or 20 years ago, or 30 years ago, or 10 years ago, well, we better learn something new today, and we better propose something new today, or something evolved. But don't spend too much energy criticizing and changing names on what was done before. If you can if we can propose something new, fantastic, let's do it. We need that. And it will happen. It's a matter of, of course, it's a matter of just letting people do the right studies and listen.
This is wise. Thanks a lot, Antonio. Filipa?
Okay, we are now in the end of the session. I would like to thank again to Antonio for this really nice presentation and this really informative talk. Bye, Antonio, and thank you once again.
Yeah, thank you very much, Antonio. Thanks for the great talk, and thanks everyone for attending. See you next week. Bye-bye.
Bye-bye.